looking at limits algebraically. So we've got this function for f of x, and it's an absolute value function, which gives us that nice v. Let's see the different ways we can find our limits. Well, first, let's find f of a using the equation. So what if we actually plugged in that x value? So if we plug in 0, we would have, so f of 0 equals 1/2. And then if we plug in 0, that would be 0 plus 4, is 4, minus 4, so half of 4, because absolute value of 4 is 4, it's 2. So f of 0 is -2. The limit as we approach 0 on the graph is also -2. So as x approaches 2 from the right, well, first let's just see what the point is if we use the equation. 1/2 -2 times 2 is -4. It's going to be 0, so we'll get -4, I'm sorry. Let's look at the graph. When x is 2, whether it was from the right side or the left side actually didn't matter, because we still got to -4. What about 10? So if I plug in 10, that's going to be -2 times 10 is -20, plus 4 is -16. That's going to turn it into a positive 16, half of which is 8. 8 minus 4 is 4. Gosh, I don't know why my brain damaged there. So what do you think would happen? Well, this graph's going to keep going, and it's going to hit that point. And an absolute value doesn't have any holes or vertical asymptotes or anything weird. It is just a nice, continuous graph. So when we have a function that is defined and continuous for all of the x values, we can actually just plug in that x value. We can plug that in as long as f of x is continuous. Which can be super easy sometimes. Sometimes it's a lot faster than actually graphing every single one of these. So let's take the first one. If we know this is a quadratic, which is nice and smooth and continuous. If I plug in 3, I'm going to have 1/2 of 3 squared, which is 9, minus 2 times 3, which is 6, plus 3. So this is going to be 4.5 minus 3, which is going to be 1.5. The limit as x approaches 3. Now, this is a rational function, but at 3, it's not dangerous. Watch what happens when I plug it in. So 15 plus 2 is 17 over 3. Easy. X approaches 2 from the left. I don't even think I care that it's approaching from the left to the right. Let's see what happens when I plug it in. absolute value of 2 plus 2, which is, not absolute, that's the square root. And then 2 plus 1. So that's square root of 4 is 2 minus 1 1/3. The limit as theta approaches pi over 2 of sine of 2 theta would be the sine of 2 times pi over 2, which is the sine of pi, which is 0. Cosine of 2 pi over 3 over theta, which would be 2 pi over 3. Well, that's negative 1/2. See, if I'm dividing by a fraction, that's the same as multiplying by a reciprocal. Let's see, log base 8 of, I don't care. We're just going to plug in. Log base 8 of 11 minus 9. And 2 is the cube root of 8. So 8 to the 1/3 would give me 2. Let's look a little bit more at this analytical approach. So what happens if we try to evaluate these using direct substitution? Well, if I plug in negative 3, I'm going to get 9. That's going to be negative 12 plus 3. And then this is going to be 9 minus 6 minus 3, so that's 0 over 0. Okay, plug in 1. 1 plus 4 plus 3. 1 plus 2 minus 3. It's going to give me 8 over 0. Uh-oh. That's not good. Well, if I plug in 1 from the right, I'm still going to get the same thing. So I'm going to end up with 8 over 0 again. So for each of these x values, the function is undefined. But could we actually find the limit? I actually can. At negative 3, look, from the left and the right, it's still going to the same place. It's going to that hole. It's going to 1/2. If I'm going to positive 1 from the left, it's going to negative infinity. Positive 1 from the right is going to positive infinity. So how can we determine that without having to graph all this? So let's think how we would have found those discontinuities, the holes and the vertical asymptotes and stuff like that in pre-calc. So the first thing we're going to do is you're going to factor the numerator and denominator. Two, if a factor cancels, there is a hole, or discontinuity, but I like to say hole. 3, if a factor does not cancel from the denominator, there is a vertical asymptote. So let's see that in play on this function. Let's factor it. It's a nice one to factor. It's got to be x and x to get x squared. Multiplies to be 3, but adds to be 4. Multiplies to be negative 3, but adds to be 2. And then let's see what happens. Well, these cancel out. They divide out. That means that we have a hole when x is negative 3. But since we divided out, we know there's a hole there. Let's see if the graph is going to a certain point. So let's plug in negative 3 now. So negative 3 plus 1 over negative 3 minus 1 equals negative 2 over negative 4, which is 1/2. Which is the same thing we got on the graph. So that's pretty interesting. Now let's think what we would do with the other part of it. So let's think back. Okay, so we have this rational function that has a non-removable infinite discontinuity. Big words, but what that means is we have a vertical asymptote. Since the y values do not approach one specific value from both sides at a vertical asymptote, then the limit does not exist. However, we need to know if we have a one-sided limit, like on the last one, if it's going to the left or to the right, or what it's doing there. So for each of those, we can still simplify the function. We can factor and simplify it. But it depends on if we're coming from the left side or the right side of what to do next. So if we're coming in to the left of x equals 1, pick a value like 0.9 and plug it in. So 0.9 plus 1 over 0.9 minus 1. What would happen there? Well, we know they're going to infinity. So all we really need to know is what the sign is. Well, the numerator is positive, denominator is negative, so the whole thing is negative. So this one's going to negative infinity. If we were coming in from the right side of 1, 1.1 is a good one to use. So plug in 1.1. Now remember, I don't really care what the numbers are. I'm just looking for signs. This is going to be positive. Denominator is going to be positive. So overall, it's going to be a positive number, which means this is going to keep going up to positive infinity. Now, could I have picked anything to the left or the right? I really could have. But the closer you are, that's going to make it a little bit more accurate. Okay, so the next technique, last technique for algebraic is when we have a square root function. Rationalization can be used to evaluate this, because if we plugged it in right now, 3 plus 1 is 4. Square root of 4 is 2. 2 minus 2 is 0. 3 minus 3 is 0. This would be a bad one if we plugged in directly. But we can use what is called rationalization. So it's a little trick. You may remember from rationalizing denominators. But if not, it's an easy trick. So, as long as we do the same thing to the numerator and the denominator, we're okay by algebra laws. So I'm going to multiply a fraction that's equivalent to 1. So the same thing in the numerator and denominator. I'm going to go with the square root of x plus 1 plus 2. And I have to do the numerator and the denominator by the same thing. Let's see what happens next. So we multiply. Square root of x plus 1 times the square root of x plus 1 is just going to give me an x plus 1. 2 square root of x plus 1 and a negative 2 square root of x plus 1 is going to go away, but I'll go ahead and write them so you can see it. Then we have negative 2 times a positive 2, which is a negative 4. Now in the denominator, I like to hold up a second. You'll see why in a second. So x minus 3 times the square root of x plus 1 plus 2. I like to get the numerator all pretty first. So let's see. These two divide out, and I'm left with x plus 1 minus 4. So x plus 1 and a minus 4, which gives me x minus 3 in the numerator. Oh my goodness, there's an x minus 3 in the denominator. Would you look at that? Those divide out, leave me with a 1 in the numerator. Oh my goodness. So now I can actually plug in the 3. Into this. 3 plus 1 plus 2. It's 4, so the square root of 4 is 2. Equals 1/4. Fancy trick.